Okay, welcome back. We've already seen how to use the light tracer to create realistic indirect illumination in 3ds Max. Now we're going to look at the second tool in the arsenal of Max's rendering and advanced lighting features to create indirect illumination. We're going to use Radiosity this time. So let's open up an example scene that I've set up for us. Hit Control O to go ahead and open up the file browser. And let's go ahead and open up the Radiosity underscore start scene. So let's go ahead and open that up. And this is what we've got. Pretty simple scene. We've got a room with an open window. And inside we have sort of this ornament or this vase. And we have these strange walls with kind of like these cubes sticking out or whatnot. And it's pretty simple. We have one light in the scene, this photometric light over here, that's casting light into the window. Okay? So it's pretty simple. Let's go ahead and before we do anything, hit Shift Q to do a render and see what we've got. So it's a 320 by 240 pixel render. Taking a little bit of a while there to render, but you can see we've got. The light's very hot, very warm color, and it doesn't look too great. To make this look better, because we're using a photometric light, what we want to do is use logarithmic exposure control. So hit 8 on your keyboard to go ahead and open up the environment window. And under exposure control, right here we can notice that we have no exposure control, and that's no good. So let's go down in this list and choose logarithmic exposure control. And that's all we have to do. Now let's go ahead and close that window. And let's close the render window. Let's get a little bit closer here, something like this, so it looks better. And let's go ahead and do a render. And now you can see that the logarithmic exposure control combined with the photometric light creates some beautiful, realistic, soft lighting. Very realistic, very photometric. Very nice. Excellent for doing architectural visualizations or pretty much anything. It's not just limited to architecture, but you can use these types of lights and the logarithmic exposure control if you're doing any type of animation or whatnot. Let's also switch from production mode to iterative mode, and there we go. We have ourselves a pretty nice render. Okay, let's go ahead and open up the render setup window. So we'll go up to the rendering menu and click on render setup. Shortcuts F10 on the keyboard for that. And let's go to the renderer tab. Let's enable SSE and let's turn off anti-aliasing so we get faster renders. Let's also go to the advanced lighting tab and let's go to the drop down list. We're not going to use light tracer, we're going to use radiosity. So go ahead and turn on radiosity. And I'll move the render setup window over here to the left and place this rendered frame window over here in the center and to the top. Okay, so there we go. Now we have radiosity activated in our scene. So let's go ahead and let's render again. And you'll notice that nothing changed except of course for the anti-aliasing. It still looks the same as before, so what in the world happened? I'll explain that in a moment. Right now let me close these windows. I'm going to go ahead and swing my camera around behind the vase over here. I want to get camera angle from about right here is pretty good behind the vase so I could see this dark area right here. Okay, and let me perform a render from here. You don't have to place your camera exactly where mine is. As long as you can see behind the vase and behind that wall back here, you'll be good to go. Okay, so this is what we have right now. This is basically just direct lighting. We don't have any indirect illumination like what you would expect in the real life and in the real world. Basically, lighting is coming off of the photometric light through the window and hitting this wall here, and it's hitting the floor in this object here, and that's pretty much it. Well, this is very unrealistic because in the real world, light would bounce off of these objects and these walls and the ceiling and the floor, and you would be able to see something back here. It wouldn't be pitch black like this, like if we were in outer space. And even in outer space, you'd probably be able to see behind this object because of some very dim starlight coming from nearby stars and things like that. So this is unrealistic and it's unacceptable. So let's use the radiosity in 3ds Max to fix that. So let me go back and open up the render setup window. Again, I'll move it over here to the left, reposition this right here. Okay, let's go to the advanced lighting tab and let's start to explore the radiosity in 3ds Max. Now, just because I activated the radiosity doesn't mean that it's going to work right off the bat. Radiosity has to be calculated first when we're going to perform a render. So before I explain anything else, let's just do that. You notice this button up here says start. Well, let's go ahead and click on that. And you notice that the radiosity processes, and you can see the progress here, and then it finishes. When it finishes, You'll notice that now you can see this lighting, this sort of ambient lighting in the viewport, and you can also see that the objects have been tessellated. What that means is that the objects have been broken up into smaller polygons. As you notice, this is not how the objects looked before. Now there's these extra edges and lines on the objects. They've been tessellated. Now if I perform a render, you'll notice that I have indirect illumination. Now I have light bouncing off of objects and lighting up the dark parts of the scene. Of course, the quality is extremely low right now. The accuracy of the lighting is very low. And we have this light blotching on the back of the vase that looks very nasty. This is a preview render. This is doing this at 85% quality, as we can see here. And it's a very rough preview render, which can give you a good idea of how the overall lighting is looking in your scene, which is a good thing. But now we have to work on producing a higher quality image here, a higher quality radiosity solution to get this looking much better. So how do we do that? Before we can do that, you have to understand how the radiosity system works and how it goes ahead and fixes the quality of the render. Basically, this is how it works. The radiosity is calculated, and the radiosity solution goes through 4 different quality phases. In this video, we're going to talk about the first 3 quality phases. We'll talk about the 4th and final one in the next video after this one. So I've broken this up into 2 videos because it's a lot to cover. Okay, the first phase of the quality process of this render is going to be the initial quality. Pretty self-explanatory. So the initial quality is set here, and it's a percentage. So the higher the percentage, the maximum is 100%, the higher the quality of the render is going to be, but the longer it's going to take to render. So if I lower the quality to, say, 50%, the quality is going to be really bad. But the render is going to be faster. The process of radiosity is going to perform even faster. When I switch it to 50%, I can hit continue, and I don't have to recalculate the entire radiosity solution again. This is because the radiosity is it's pretty cool in the sense that once we start doing radiosity, we can increase the percentages, and we can just hit continue as opposed to calculating it from scratch all over again. But even that process is pretty limited itself. So if I go back to, say, 85%, that was the default. So let me instead go to 90%, and let me hit continue. The radiosity solution is calculated very fast, as you can see. That's because it picked up where it left off, and it left off at 85%. So if I hit render again, you notice now that the solution comes out a little bit different, a little bit improved, but we still have some variation there in the lighting and things like that. So that brings me to the second phase of improving the quality of the radiosity solution. So that was the first phase, initial quality. It's the simplest and easiest phase to use because you just plug in a number and percentages, and voila, there you go. The second phase is the refine iterations. Now we have 2 options for refining our iterations, and I'll explain what refine iterations means in a moment. We have the all objects and the selected objects. So what does refine iterations mean? Basically, refine iterations is a fancy way of saying breaking down your objects X number of times. So if I close this render frame window, you can see that, like I pointed out before, when we calculate the radiosity went ahead and broke up all the geometric objects in our scene into smaller triangles. So we could see this polygon here was broken up in half. You can see this edge that cuts it in half. And most of the polygons here were cut up into smaller pieces. In some cases, they were broken up into 2 pieces. In other cases, they were broken up into more. Okay, the refine iterations controls how many pieces things are broken up into. So what we can do is we can select over here in the refine iterations all objects. We can increase the number from 0 to 1 or 2 or 3 or more. Now the higher the number of iterations, the more the objects get broken up into in your scene. So we'll have objects broken up into little tinier elements. Now the good side to that is that the render is going to come out nicer and higher quality. The bad side is the calculation of the radiosity is going to take longer to do. So that's one thing to keep in mind. So let me just put this back to 0. So that's the second phase. So when you want to refine this even more, make it look better, you increase the iterations here and things start to look better. And I could actually do that just by increasing that to 2, hitting continue, and then hitting render here. And you notice that now this looks a lot better. Most of the light blotching went away, and our scene looks a lot better. right off the bat. So that was the second phase of improving the quality of the render, and it didn't add a lot of rendering time because fortunately we're able to use this continue button. Now, refine iteration selected objects works a little bit differently, but very much similar. The way it works is just like the all objects option up here, except that it works based on which object you have selected. So if I select an object like, let's say, the walls here, and I increase the iterations on that to 2, and I hit continue, the Radiosity engine will try to go ahead and refine the wall back there. So we'll see if it made an improvement. And it made very little change, if any. At this point, I have to ask myself, what can I do to improve the quality of the render? Well, it's time to move on to the third phase of the quality. So, where's the third phase? Down here you see a parameter rollout called Radiosity Meshing Parameters. We'll open that up simply by clicking on it. And this right here is the third phase of the quality of the Radiosity solution. This is the global subdivision settings. Right now it's set to disabled because the enabled flag here is checked off. Okay, that's the default. The reason that's checked off is because once we check that on, our render times are going to increase by a good amount. Okay, you'll also notice, let me turn that off. Notice up here, there's no message. As soon as I enable this, a message pops up and it says solution is invalid at current time frame. What that is trying to tell us is basically, look, you turned on this new option down here, this enabled option for global subdivision settings, and that's going to go ahead and force me to have to recalculate the entire Radiosity solution again from scratch. So the current solution is going to be no good. We have to go ahead and reset all and then recalculate the solution because you activated this option. So that's okay, and that's what I meant by earlier when I said that this continue button is pretty limited. It works well when you're working with the initial quality and even with the second phase here, the refine iterations, the second phase of quality. But once you get into the Radiosity meshing parameters and you start playing around with those, you have to reset all and recalculate from scratch. But that's okay because it won't take us too long to do that. These are the default settings. Use adaptive subdivisions turned on, and I'm going to show you how it works simply by going here and hitting reset all. And Max is going to go ahead and ask us, are you sure you want to reset the Radiosity solution? I'll hit yes. Okay. And I'm going to lower the initial quality back down. I'm going to go to something pretty low here. Or I'll just knock it down to 85 just so it goes a little bit faster. Refined iterations, I'll leave it at 2, that's fine. And I'll hit start to begin the calculation. And it's going to go ahead and it's going to calculate, it's going to do its processing and think about the whole thing. And in this case, it didn't take too long. Now you'll notice that the walls and the floor and the wall up here on the top were broken down and they were tessellated differently. So what happened? Well, we used adaptive subdivision because we have it checked on down here under the Radiosity meshing parameters. So it's using these 4 settings here: maximum mesh size, minimum mesh size, contrast threshold, and initial meshing size. It's using those 4 settings to determine how it's breaking down our scene this time. Okay, now the good side to using adaptive subdivision is that it can increase your render times dramatically, really, if you go ahead and set up these settings correctly. And if your scene, well, your scene will usually work pretty well with this. Actually, just edit that out of the video, edit that out of the video, starting again in 3, 2, 1. So using adaptive subdivision can help you get a very substantial boost in your render time, so you can render faster. Okay, it's just a matter of understanding how these 4 settings work together, so allow me to explain that right now in the next few minutes. The first setting here is maximum mesh size. Right now it's set to 1 meter. This basically tells 3ds Max what's the largest area that can be broken down into smaller triangles. The larger this size is, the faster the render is going to be, but the lower quality and the less accurate it's going to be, so it's a trade-off. Smaller number equals better quality, slower render. Larger number equals less quality, faster render. So it's just something to keep in mind. The minimum mesh size is going to tell 3ds Max how small it can break the meshes up. In this case, to a size of 0.1 meters. The contrast threshold is going to work by helping the renderer to determine which areas need to get broken up more. Let me show you visual representation here. if you look at the floor of our scene here, it's broken up into a lot of triangles. If you look at this back wall right here, you'll notice it's only broken up into 4 polygons. This one, this one, this one, and this one right here. So why is this wall being broken down only into 4 polygons and this floor is being broken down into a lot of little triangles? Well, the contrast is controlling that. It's set to 75, which is the default. The contrast is basically telling the Radiosity engine, look, the floor has more contrast and has more stuff going on it, so we're going to need more detail out of it. To get more detail, we have to break down the floor into smaller triangles. This back wall isn't getting a lot of detail. It's not getting any shadows or anything. It's kind of just sitting there and facing the dark side of this corridor right here, which means that it doesn't need to be broken down into too many triangles. Because if it did, it would really be a waste of calculation and time and processing power to have to calculate this if you really didn't need to calculate it and break it down into so many little triangles. So it's very important to understand that concept when you're using adaptive subdivision. And then the initial meshing size is just going to tell the renderer what is the initial size that it can break up the meshes into. Okay, so using smaller numbers is going to create, again, nicer renders, but going to take longer to render. Larger numbers are lower quality renders, but render faster. Alright, so this is adaptive subdivision. Now, if I turn off adaptive subdivision, I've just activated the regular global subdivision. What it's going to do now is it's going to go ahead and break down the entire scene based on one parameter. And that parameter is the maximum mesh size, which is set to 1 meter right now, which is too big of a number. So I'll set it to 0.1 meters, okay? You'll notice that my solution is invalid right now, so I'm going to have to reset all, hit yes to confirm, and hit start to recalculate. Now what it's going to do is going to break up the entire scene based on the maximum mesh size of 0.1 meters, which means that this thing is going to be broken up into lots and lots of little triangles. The downside to that is, as you can see, we're taking a little bit longer to render out the Radiosity solution. The upside, this thing is going to render out at a nicer, higher quality. Okay, so there we go. It finished calculating the Radiosity and it broke down the mesh. As you can see, the mesh is now broken up into literally thousands and thousands of triangles. Again, the downside was that it took longer to calculate. The flip side to it is that the render quality is going to be a lot better. So if we go ahead and render that, now you notice that my lighting is a lot more accurate. Yes, we still have some light blotching, that's okay, but the shadows and the lighting and the intensities and energies of light bouncing around the scene looks much more realistic and more natural. So that's the advantage of breaking up your meshes, the Radiosity mesh, into smaller triangles. So, in a nutshell, to get high quality renders using Radiosity, you have to break down the Radiosity mesh, which is this mesh here that you see the objects in the scene, into smaller triangles. The more triangles they are, the more accurate the lighting is going to be and the higher quality it's going to be. Okay, but you probably noticed, okay, that's great and all, but we still have some slight light blotching in our scene. How do we fix that? Well, there's a couple of ways that we can fix that. First of all, we're using an initial quality of only 85%. We can increase that to 100% if we wanted to get a more accurate lighting solution here. Problem is, I have a feeling that there's still going to be some slight light blotching in our scene. So the way to fix that would be to break this up into even more triangles, which of course is going to increase rendering time. But I have a little solution for that. Instead of wasting time calculating more by breaking this down more and increasing the initial quality, why don't we do this? Let's use these interactive tools down here. We have two very important tools, the indirect light filtering and the direct light filtering. The indirect light filtering is going to be the most useful of the two. What it's going to do, it's going to use a filter to try to smooth out these blotching effects here in our scene with the indirect illumination, which is the light that's bouncing around, the realistic global illumination. By default, the filter is set to 0, which means that it's turned off. Let's increase the filter to something like 4, and you'll notice that when I did that, it updated the Radiosity solution. There's no need to have to go ahead and click on continue or reset anything. It's interactive, meaning that once you make the change, it updates automatically, and there you go. So now if I hit render, you notice that all of that blotching magically goes away. And now we have a nice, clean, crisp render. Excellent, right? Now the direct light filtering works as a filter but for the direct lighting. In this case we only have one direct light, which is a photometric light out the window. Right now it's not causing any type of artifacting or problems, so using a filter, as you can see, if I go ahead and add the filter there at a size of 4 just so it matches up with the indirect lighting. You don't have to do that, but I'll just do that in this case. You notice that the direct lighting here wasn't really affected by the filter at all. So in this case, it would be a good idea to turn that filter off by setting it to 0 because we really don't need it. In this case, the indirect light filter is the one that did a lot of work and helped to fix up this scene for us. So that's how you can get this global illumination to look really good. Last but not least, down here we have light settings. Now, the light settings work like so. When you have adaptive subdivision turned off, you can go ahead and turn shoot direct lights on or off. If you turn off use adaptive subdivision, the light settings option here for shoot direct lights gets grayed out and you can no longer have access to it. So what's going on here? Well, let me do some test renders so I could show you the difference between shooting direct lights and not shooting direct lights. Okay, here's what I'm going to do. I'm going to turn off shoot direct lights, and you'll notice that the solution now becomes invalid, so I have to reset all. Hit start, let it render. Okay, I ended up skipping ahead in the video just so you wouldn't have to watch this thing calculating. It did take about a good minute, maybe 2. Okay, so we basically calculated the radiosity without taking direct lights into account. So let's perform a render to see what happened. The render becomes a little bit darker, and it looks a little bit different in terms of the light intensity. This is because right now I told the Radiosity engine not to take direct lights into account when it performs the calculation. This isn't a good thing to do. The reason for that is because you want the direct lights to actually contribute to the overall global illumination in the scene. There's no reason why you wouldn't want to. It's best to have it calculate. But the option's there in case you don't want to do it or you do want to do it. It's really up to you. So I'll go ahead and turn that back on, and that'll invalidate my light solution. That's okay. And then down here we have different options. These 3 options here include point lights, linear lights, and area lights. Basically just tells the Radiosity engine, look, when you calculate radiosity, take into account point lights, take into account linear lights and area lights. Point lights are lights like spotlights and omni lights. Linear lights are lights like directional lights and sunlights. And area lights, of course, are those nice area lights that take so long to render but look great. Then we can also include skylights if we have any in our scene. In this case we don't, so this option is pretty much irrelevant in our case. And then down here we have include self-emitting faces and subdivision. What that's going to do is any faces or elements that are self-illuminating will be taken into consideration when the calculation is being performed for radiosity if we turn that on. If we turn it off, then it doesn't matter. Okay, so these are the default settings. I recommend keeping it. Default settings are pretty good, but of course if you want to turn on skylight you can, and self-emitting faces you can as well. Okay, strongly recommend you use shoot direct lights at all times. Okay, so there you go. Now the final thing I want to mention is scale. It's very important when you use radiosity. Radiosity is based on physical scale. What this means is that 3ds Max is going to look at the scene scale of your scene, and it's going to determine the lighting, the final lighting output based on that scene scale. If you don't understand what I mean, let me show you. If I go up to Customize menu and I go to Unit Setup, you notice I have my unit set up to the metric system, and it's set up to show me meters. If I switch from meters to centimeters and hit OK, you notice now in my render setup window, the maximum mesh size switched to 10 centimeters. That's because 1 meter is equal to 10 centimeters. Okay, so 3ds Max is smart that way in terms of unit scale. It's always converting things, it's always paying attention to the scale, and when you're using radiosity, radiosity is paying very close attention to the scale of your scene. So if the scale of your scene is disproportional, your lighting's going to look disproportional too, I'm afraid. So if you're doing an interior scene, say a kitchen, and you have a dining table or something with maybe some chairs, make sure that the chairs are the same size in your scene as they would be in real life. So if you have a table that's half a meter tall, make sure that the table, okay, is half a meter tall in max as it would be in real life. That's one thing that you have to really make sure about, because Max will take that into account. So I'll go back to the customize menu, go to unit setup, and switch this back to meters. And if I go to system unit setup, this is where you can tell 3ds Max how many units are represented here. So in this case, I have 1 unit equals 1 centimeter. 1 unit equals 1.0 centimeters. You can switch centimeters to inches and feet if you like the English system, or centimeters and meters if you're going to be using the metric system. So I'll go back to centimeters, and you can see 3ds Max is constantly updating every time I change that, because it has to be looking at that scene scale, because the scene scale is going to play a vital role when it comes to radiosity. Okay, so there we go. That's going to cover it for this video. In the next one, we'll continue and pick up where I left off here and finish up with the with this first example scene of radiosity.